So welcome everybody. Thanks for joining me this evening. Basically, what I'm going to do is talk about climate change, the climate crisis, and the impact that's having on a sustainable future for societies across the globe. My name's Dan Parsons. I head up the Energy and Environment Institute at the University of Hull. So, when I talk about global climate change and issues related to sustainability, I like to use this photo to begin with. It was taken from the Apollo missions, from Apollo 8. Looking back, it was the first Apollo mission that went round the backside of the moon and came back. It was actually looking for landing sites on the moon, and the astronauts on the way round took this shot of what's become known as Earthrise, to photograph Earthrise. And why this is important is it really began to put, for people on planet Earth, the perspective of where we are, where we sit within the universe, and that we sit on this blue sphere in the middle of space, and it really crystallized the environmental movement around issues to do with pollution, but then more latterly global climate change, and it really was the birth for that movement. And perspective is incredibly important when we think about global climate change. On a nice sunny day, we don't get many of them in Hull, but on the ones that we do get, when you look up to the sky, it seems limitless and vast. But actually, when you look from a different perspective, and this was taken from the International Space Station, you can see that actually the atmosphere is this thin veneer around our planet, and actually all life that we know of in the entire universe exists within and is supported by this really thin veneer. So when we think about the atmosphere and you know that's you know, it's not limitless. There's actually, you know, a volume there that supports us. We also think about water as well. So I just want to try this, see if this works, and run a little bit of a poll here with you guys there. So if you would input menti.com into a browser, or indeed scan the QR code there, what you'll be able to see, hopefully, is a guesstimate comes through. Hopefully you can all see that. I'm just checking with Maria that this is working, and you can see the Menti window at the moment. As you all come through on there, if you log on, use the code 4647463, you'll be able to input your guess to what percentage of the Earth is covered by water. So we're looking, yeah, the people are flying in here in terms of, okay, it's pretty unanimous. That's really good. Okay, I've got all of you. Wow. I think all of you managed to do that. I know, keep them coming. We'll come back to them. I think there's 2 people that haven't managed to yet do that, but yeah, it's great. Thanks for that. Well, it turns out, yeah, you're right. It is 71% of the surface of the Earth is covered by water. So let me see if I can get back to the PowerPoint presentation. But what percentage of Earth is actually covered by water? So we've done the covered by water, but what about the actual percentage of Earth that is how much of Earth is made of water? Is probably the better way of thinking about that. So yeah, let's do the same again there, and I'll pull this across when I get it. So do you want to go ahead and fill in the same way? You should be able to see my my screen there. Okay, people coming through. Sorry about that. I'm just trying to work out how to move it forward. Okay, so the lower end here. Couple going for 20%. Low end. So some votes coming through. So actually, there's 0.2 is winning at the moment. So actually, when we look at Earth, and this is again down to perspective. What we can see here is a ball or sphere of Earth as a rocky mass with all of the water brought together. Now the three discs that hopefully you can see there, if your screen's big enough, the biggest one is all the salt water on Earth, and brings all of that together. The round circle is all of the ice and the water in the atmosphere. And the smallest little sphere there is all the water in lakes and in rivers at any one time, and it is 0.02%. So although we're called the blue planet, we should actually be probably called the brown or the rocky planet. And the water that we have here isn't limitless. So you think about the amount of heat that we're putting into the atmosphere, or plastics, or any of the contaminants that we release into our atmosphere ends up in the ocean. That's not an infinite water body that we're polluting, and that has some real significant impacts for society and sustainability into the future. So again, perspective is really important here. So the next one I want you to go at is what comes into your mind with global warming. So the menti.com link on this one is very much let me do this one. What comes into your mind when you think about the issues to do with climate change, and what does it mean to you? So go ahead and fill that one in, and we'll see what comes up when we bring that through. So you should be able to type in free-form text, and it should create a word cloud for us to really think about what climate change means to you, what global warming means to you, and what the thought processes are around those. So hopefully you guys should be able to get in and do that. Yeah. Great. So words are extreme weather, pollution, deprivation, social deprivation, extinction, unnecessary, warm, wet, apocalypse, sustainable energy, rising sea levels. Great. Okay, so there's lots in here coming through. Pollution, ice caps melting, scary. Excellent. Oh, this is really good. This is working really well. Great. So you can pick up some of the things there that are coming through. Thanks, folks. Government denied. Okay, yeah, good. So lots of issues there around policy and politics. Discriminatory, great. So really thinking about that social justice angle. Really good. So let's move on. Right, so when we think about global warming, people use these phrases interchangeably, climate change and global warming. Well, what do they mean, and can they be used interchangeably? Well, global warming really refers to the warming of the planet, and I'll talk about that in a minute and how that works. And the evidence I'll present to you, the science that sits behind this, is that we know that global temperatures have risen since the early 20th century, and you know, since 1970s, 1980s, it really has ramped up in terms of the increase in temperature. So it's really begun to crystallize in a range of impacts that I'll talk about, and there's been about a 1 degree rise in temperature over that earlier baseline from the mid 20th century. So that's what global warming is. Climate change is because of the result of the global warming. Climate change is the result of that warming. So the patterns of weather that we see, the average weather patterns, how are they changing? So climate change is broad and a general term for the changes that are a result of the global warming, or global heating, as some people now call it. And this is causing all sorts of effects like more powerful hurricanes, more frequent flooding, accelerated ice melt, sea level rise, and indeed some of the social things that some of you raised a moment ago in terms of worsening vector-borne diseases, impacts on social deprivation, food security, water security, and all of those things that again I'll touch on later in the talk. So let's go through, to begin with, just a little bit of the science that sits behind this. So the Earth receives solar radiation in the form of light waves that come through space and pass through the atmosphere. Now, most of that radiation is absorbed by the Earth and warms the Earth up. But some of the energies actually bounce back out into space. About half of it is basically reflected back out into space. But some of the outgoing infrared, so some of the, once Earth warmed, it then radiates itself back out. And this is basic physics. Warm bodies radiate out heat. It's like putting your hands around a warm mug and just holding further away. You can feel the heat radiating out from it without touching it. Now, Earth does that, it radiates out heat. But what's happening is that as we increase the thickness of our atmosphere, effectively in terms of trapping gases in the atmosphere, the CO2 concentration or methane concentration increases. More of that outgoing infrared radiation is trapped in this greenhouse effect, and that's where the terminology really comes from. And as a result of that, that's driving the warming that we see. So nearly half the solar energy that reaches the top of the Earth's atmosphere is absorbed by the planet's surface. And if you think about the amount of energy, and again, we've been able to work this out through monitoring studies, and indeed since the dawn of the space age, we've been able to take measurements in space to quantify all of these sorts of things. We get to about 340 watts per square meter of solar radiation. Now, you think about your 100-watt light bulb, for example, and the sorts of, you can start to think about a meter square and what that looks like in terms of the energy received. Now, 29% of that is reflected back into space, 23% is absorbed by the atmosphere, 48% is absorbed by Earth's surface. But what happens is, as that Earth's surface warms up, it radiates that back out, and it actually releases more than it receives. And this is where some of the really interesting science comes in, because effectively about around 400 watts per square meter gets re-mediated out, but of course it's reabsorbed by the atmosphere and rebounds back up and works as a blanket. So it's about the heat re-irradiating backwards and forwards in the atmosphere, and that's how Earth effectively re-irradiates more than it receives. But ultimately, that's what keeps and maintains a stable temperature on Earth's surface, or has done for the past few thousand years. But we're spewing out colossal amounts of global warming gases into this thin veneer shell that I showed at the start, and that every 24 hours it's 152 million tons, and that's thousands of atomic bombs worth of energy that we're essentially releasing out into the atmosphere in terms of warming. But when we think about those gases, I'm going to move back to Menti here and just see what do you think those sources are? What do you think those greenhouse gases actually comprise of? What do you think that those things are in terms of the atmosphere? So I'll go to the next one. I'm getting good at this now. Look. So what are the main sources of greenhouse gases? So again, it's a free text one. You should just be able to type in the sorts of gases that you think cause the greenhouse effect. Oops. So hopefully that should be live for you folks. Perfect. So yeah, fossil fuels, so the gases from fossil fuels, burning coal, aerosols, CO2, so carbon dioxide, that's right. Methane from cows, that's right. Aerosols is an interesting one I might pick up later on in terms of the impact that has. Sulfur dioxide, humans, power plants, meat industry, farms, water vapor, combustion. Excellent. So really good. Deforestation, land use, excellent. So yeah, some really good things in there. Transportation and cars as well. So excellent. Thanks, folks. You're right, you've picked up lots of them. So these are the biggest sources of greenhouse gases. You can see industrial processes, coal plants, coal mining, permafrost. Thawing of permafrost is releasing out some of the methane from those environments, air transport, oil production, burning forest fires, landfills actually in terms of the methane and the rotting away of our waste as well, transport, fertilization, farming, industrial agriculture. So they're the primary drivers of greenhouse gas release to the atmosphere. I think we got most of them there. Now, the important piece here is that this is increasing. The largest source is the burning of fossil fuels, and since the 1850s, when we discovered oil and really began the industrial revolution in terms of powering it from fossil fuels, we've seen an exponential increase in here we've got metric tons of carbon burnt effectively since 1850 through to very recently, and you can see that lift up, and indeed now, half of all carbon emissions are being emitted in my lifetime. It gives you the kind of scale of the problem that we've created for ourselves over, actually, I'm not that old, so relatively recent past. So real exponential increase of billions of metric tons of carbon that we're releasing into that atmosphere. And when we look back, and I'm a geoscientist by background, we look back into Earth's history, and I'll tell you a little bit about how we do that in a moment in terms of the geology. We can see that actually for millennia, in fact, since 66 million years ago when the dinosaurs were wiped out, have we had carbon dioxide levels at the levels that we have today. So we've really changed Earth forever in terms of the release of carbon dioxide here to really high levels. So this is having a profound effect, and I'll talk about those at the moment. But I wanted to put that long-term trajectory there in focus, and indeed, if we go back to 500 million years here, so here we've got average temperature variation from the 1960-1990 average, and then that's related back right the way through to 500 million years ago through a series of panels. What you can see is actually the temperature uplift that we've got here on the right hand side of your graph projected to 2100 takes us into warming that we've not seen for well over way back into the Pliocene, so back to 3 million years ago. So we're really talking back into long distance past in terms of the CO2 levels and the temperature that's resulting in. And we can zoom into the more recent past of the Holocene, and this is where hominids, where humans have evolved and lived on planet Earth in this small little window at the end of this geological time clock here, very stable until very recently. And this is what we're really worried about when we're talking about the climate crisis, is this massive uptick after a long period of stability. And again, just zooming in a little bit more in terms of what we're seeing in terms of this rapid uplift, this hockey stick of temperature, and we can see we're up at 1 degree of warming average globally, and that's having a really big impact. Well, how do we recover some of these things? So, and we're going to go into the detail here, but how do we know? Some of the work that the scientists I work with and others use ice cores to go back for around 1 million years, something like that. What we can do is take the pockets of air that are trapped within ice cores, so snowfalls, gets compressed, traps the air. We can take samples of that air and work out isotopic ratios, that's the weight of different molecules, and we can work out from that the balance between the amount of water that was in ice form and the amount of water that was in liquid form at that time, from the different ratios of isotopes, because ice tends to have lighter isotopes contained within it, and as a result of that we can reconstruct temperature. Now it comes with uncertainties, but we get it there, we get it right there and thereabouts, and there's various other indices that we can use and other ways of getting at the same information. We can cross correlate and check all of that out, and that's what builds these sorts of graphs, and what sits behind the uncertainty, the grain bands here, behind those different things. But even with those uncertainties quantified, you can see this uptick at the end is very, very large. So what's this happening? What's this warming doing? So here what I'm plotting is a deviation from the mean. So how everything's changing from the average and how often that's happening. And we've got this kind of, I guess, this French flag here that's kind of demonstrating this. So this is the summer temperatures from 1951 to 1980, and this is plotting it. It's a normal distribution, so we have outliers that sometimes the summer temperature are a bit warmer, sometimes they're a bit cooler, but on average they sit on the mean. But what's happened as we move through from that 51 to 1980 baseline, we can see that the warmer temperatures have become more frequent. And the whole distribution has shifted to be warmer than average and into the extremely hot. And as we continue to do this, you can see the entire shift of, now we still have cold days, days that are colder than average during the summers, but we have these extremes that we never used to have as a result of this shift in the distribution. And as a result of that, and this continued warming of the planet, we're really beginning to spread out now. Still, even with most recent, we still have colder than average days, colder than average summers, but we are on average, in general terms, having much more frequent extremely hot periods of time during the summer. And that's happening globally. It's happening at different rates in different places, but it's happening, it's having an effect all over the place. And this is similar plots that hopefully some of you have seen before, just plotted in a slightly different way to show that warming trend. So global surface temperature average departures from the average, and how that's changed over the last 200 years or so. And you can see that warming trend as we move through time. The temperature has increased as a result. And this is manifest in terms of the records that we're seeing. You'll see that if any of you read the Daily Express, you'll see a weather record every three days. But I mean, it's coming through in terms of the science data as well. And what we're seeing is all sorts of records being broken, and the 19 of the 20th hottest years on record have happened this century, and 5 of the warmest have been the last 5 years. And it's happened in the UK as well, all over the UK. These are the climate stripes from folks in Reading. Real nice way of visualizing this, taking temperature records from all over the UK and showing that this is happening from Stornoway to Oxford in terms of the impact that it's having. And of course, we see this in the news. We see temperatures and extremes in Europe. Last year in 2019, we had record temperatures, 40 degrees in Belgium, incredibly hot periods of time, and that's having a profound impact on all sorts of things. Earlier this year, the heat waves in Australia, extreme heat waves, massive heat, records breaking all over the place. They had to, the Australian Meteorological Agency had to come up with new contour scales for the heat that they needed to display on the graphics for the weather forecast at night. And of course, that had massive impacts in terms of fires and raging fires at that, displacing thousands of people and burning hundreds of thousands of hectares of land. So real big impacts as a result of this, and all sorts of things for air pollution and health, etc., etc. But it's not just happening in Australia. Indeed, just a few months ago, this summer, Siberia, up in the polar Arctic, temperatures over 38 degrees C. So some crazy temperatures in the north, and this is all the result of changing weather patterns as a result of the increase in temperatures from global climate change. But look, most of that heat that's going into the earth and being trapped is actually being absorbed by the ocean at the moment. So around 90 odd % is actually trapped by the ocean. That's having a whole range of effects. I won't go into them all, but all sorts of things from acidification and warming of the oceans, changing all sorts of things in the ocean that you know, lots of people are trying to understand the impacts of. But you can see the sorts of things again, similar to global atmospheric temperatures. We're getting the same sort of patterns within the ocean as well, if not a little bit more worrying in terms of the trends that have happened there. And again, the trajectory is really being set, and that's happening throughout the whole ocean depth. So right the way down to, you know, abyssal depths, that heating is happening right the way through the ocean, and half of this has happened in the last 20 years. So really rapid heating of the oceans. And of course, the impacts that's having is in terms of evaporating moisture into the atmosphere. So hopefully many of you will have heard of the water cycle or the hydrological cycle, and we know that the water vapor is transported across through our atmosphere. And of course, that makes up this hydrological cycle. We have evaporation, drives precipitation, water returns to the sea, and we have evaporation again. And of course, this hydrological cycle is being shifted and changed as a result of the increased temperatures. And the impact that's having is profound. So this is Hurricane Haiyan. This happened a few years ago. It struck the Philippines. I was actually working in Vietnam in the Mekong Delta at the time when this came across, and the impacts even there, you know, as it broke down into a tropical storm were profound. The Mekong rose by about must be about 8-9 meters within 2 days when we were there. It was just incredible. But this was a category 5. There is no category 6. If there was, this would be a category 6 storm. It smashed into Tacloban in the Philippines, caused utter devastation to the population there, killing hundreds, if not I think maybe thousands of people with a direct strike. It was the strongest storm ever to make landfall at the time. And this is the thing, these storms are getting stronger and they're getting more intense, and that's because of sea surface temperatures. So sea surface temperatures are getting higher, and this is where these hurricanes, these major storms, get their energy from. This is what drives them. And Hurricane Harvey a few years ago was transporting across, was forming across the Gulf of Mexico, where areas were 4 degrees warmer than average, than normal. And that drove the colossal size of Harvey and made it possible to hold the amount of volume of water that it essentially dropped then on Houston. So just stepping back out into Menti, I wonder if folks wouldn't mind just then thinking about the costliest types of natural hazard related disasters, so disasters from natural hazards. So what do we think are the costliest types of hazard? And I've just selected a few here. Of course, there are a range of other hazards that won't have been captured here. So if you're coming through for floods, storms again, okay, even pegging here. Great. That's. I'm just going to move on in the interest of time. I will come back possibly at the end to kind of look at these just as people coming through. But yeah, thanks, folks. We'll just carry on with that for the moment. So actually, it depends on how you measure cost. So what went on in your mind? I mean, I could have asked loads of Menti questions here. It'd be really interesting. But were you thinking cost in terms of pounds or dollars, or were you thinking about deaths? Because how you measure the cost of these disasters changes depending on the outcome, the order. It changes depending on how you measure it. Now, in terms of the costliest in terms of finance, they tend to be earthquakes, but the really big ones are very, very infrequent. The 2 costliest storm events were Hurricane Harvey and Hurricane Katrina, both hit the Gulf of Mexico. Of course, lots of assets there that are expensive. But there are all sorts of hazards that are related to deaths as well, and drought drives lots and lots of deaths. But increasingly, and what we're seeing over time is the impact of floods coming in and out, and there's all sorts of matrices here that people study and study in detail, and of course we're getting better at predicting these things and getting people out of harm's way, but we're also seeing more frequent climate related disasters as well. So it's trying to work out you know, the protection, the mitigation of these events on the lives and the livelihoods of people is a real science, with lots of people working on this. But really interestingly, I think, is how we perceive risk, how we think about disaster. And these data show really nicely that to get the attention of the world, you have to have a significantly higher number of deaths related to drought and food shortages than you do a storm event. So 280 people die from a storm, and you know, it's front page news. 40,000 people die from food shortages, and it doesn't make the headline news. And I think there's some really interesting areas here in terms of thinking about perception of risk, but also understanding where some of these things interface. And flood and food shortage and drought are all interlinked in terms of the impact of climate and the impact of climate change on society and social justice. And it also begs the question of, everyone's probably heard of Hurricane Katrina and Hurricane Harvey. How many have heard of Amphan that hit Bangladesh earlier this year? Struck into the Sundarbans, colossal damage. The Ceylan intrusion had a massive impact in terms of farming and food security in the region. Hundreds of people died, and it was, you know, May this year, right in the middle of COVID, and yeah, barely made the news really in comparison to other hurricanes like Maria last year in the US. So again, our perception of risk and where it happens across the globe is a really important piece. It's also affecting us here. So this we're not isolated in the UK. This is Ophelia, an extratropical storm, was a hurricane, moved across us, and indeed was effectively a Category 1 hurricane as it was approaching Ireland, which is completely unprecedented. These storms of this scale do not make it across the Atlantic this far, but because of the warmer oceans, they're beginning to, and it's starting to affect us here in terms of the intensity. And the intensity is, this is a fantastic image of a big cloud burst effectively dropping its entire content on Phoenix, Arizona. Love this photograph, but it really shows the power that the atmosphere can hold, and as we supercharge it with heat, it can hold more of this power. Again, it's really affected us in Hull and the Humber. This is from the 2007 floods. Some of you will recognize this as Newland Avenue. You know, incredibly bad floods in 2007, summer floods, really drove complete changes in policy of flood policy in the UK. Lots of research done here at the university that fed into the PIT review that came out of this, was all about how we manage flood risk and how we needed to change as a result of our infrastructure not being able to cope with the amount of water that rained on Hull over a 24-hour period. And of course, lots of the infrastructure works have now gone in terms of the storage facilities up and around in the East Riding is there to protect Hull from events like this into the future. You see these sorts of images quite frequently now, and this is from intense rainfall events, really driving microbursts and rapid surface water flows. You can see the sorts of impacts these are having in terms of the pieces from the side. So when we're thinking about flood frequency and magnitude, we need to think about the 1 in 100-year flood, the 1 in 1,000-year flood, the 1 in 10,000-year flood, and the sorts of quantification we have on that sometimes isn't very helpful. So floods are typically characterized in these manners. But what we're referencing there is the probability of floods. So what's the chance of that flood happening in a given year based on the historical average? So a 1 in 100 year flood has a 1% chance of happening annually. But you think of it in a different way in terms of your mortgage being a 30-year mortgage. Effectively, what you're saying is there's a 25% chance you will flood in your home during the tenure of your mortgage if you live in a 1 in 100 year risk zone. And that changes the dynamic for some people. 25% risk sounds different than a 1 in 100 years. When just kind of thinking about these extreme events that are happening, I showed you the shift in temperature. Same things happening in terms of extreme events. Downpours, severe downpour events are happening more and more frequently. And indeed, there's 18 1 in 1,000 year flood events that happened in the US and globally since 1980. So what's happening here is that the baseline has changed. What we're comparing a 1 in 100 year flood event to in terms of the historical data, we've changed the dynamics, we've changed the physics here, and these measurements are not stationary, they're changing over time, and these events are getting more extreme. The same sorts of things are happening in terms of ice. This is a video of the North Pole ice mass, and you can see the sea ice is shrinking over time as we move forward. Less and less of that is staying there over time, and the colors as it moves through. Yeah, old ice is really white. New ice is the darker colors, and essentially we're turning over the ice more quickly, and we've got less of it through time. You can see the differences. And so we've had massive declining ice mass across Greenland. You can see the gigatons of ice around for each of us. Essentially, it's a big block of ice around for everybody on Earth. Just to put this into perspective, it's a block of ice that's 27 meters by 27 meters by 27 meters for each one of us. And that gives you the volume of ice that we're losing across our polar caps and across areas like Greenland. So massive volumes of ice have been melted and released into the ocean. And indeed, it's melting 4 times faster than we thought. And recent research that came out last year that's really begun to kind of question some of the melt rates that we've been putting into our models, which again put us at the upper end of some of our predictions in terms of what we were worried about in terms of sea level rise as well. Other things that are happening, so this is ice streams, so where the ice flows on Antarctica, and you can see you have these streams of ice in glaciers moving out over the ice shelves and moving into the sea, and of course snow comes down and you have this cycle. Now what's happening is that areas around the margins of the ice sheets are being melted from below. This is Thwaites Glacier, a big project out there working on that at the moment. The British Antarctic Survey, joint with folks in the US and New Zealand as well, I think, working on this, trying to understand the stability of this ice shelf. And what the real worry is that where these ice shelves are pinned, they get floated off, they melt away, and it releases that stream that I've just shown you behind it. And the size of these, this Thwaites Glacier is about the size of Florida. And the worry is that if that decouples, then essentially you release all the ice that is buttressed up behind it, and you get a mass de-wasting of ice. And some of the predictions of sea level rise are based on that, and some of the uncertainties are as well. So some real big science going on, trying to understand this and trying to understand the potential impact that this may have. And of course, the impact where it really comes into it. So populations at risk of sea level rise by 2070. Look at the numbers here. So this is millions of people at risk at Calcutta, up near 15 million of people at risk from sea level rise. And the size of some of these cities, the mega cities of the globe are really at risk of sea level rise over the next 50 years. And lots of this sea level rise is locked in. Even if we reduce CO2 to nothing tomorrow, we're blocked into the warming that's already happening. It's like a big tanker that, it takes time to turn around. It's a bit like some of my colleagues at football when they turn around to chase the centre forward. It takes them a while to turn around to chase after them. And indeed, some places where I've been working, this is the Mekong Delta, home to 18 million people. Lots of this is just a few meters above sea level, and massively at risk of sea level rise in terms of an entity, and it feeds into all sorts of things I'll just talk to you briefly about in terms of food security, because the Mekong Delta is a very fertile part of the world. It's the breadbasket of Southeast Asia in many ways, and it creates massive export of food, and that landscape is at risk from sea level rise. So I've talked you through the science, some of the impacts, some of the potential changes in terms of the hazards, but ultimately the global climate change crisis is not a physics problem. It's a societal one, and it's a social justice issue, and the impact that the global climate change will have on food supply, on water, on global health are profound, and create all sorts of political and societal instabilities, and this is why lots of this needs lots of social science, lots of ways of communicating this problem to a broad range of people. So the same heat that's evaporating more water from the ocean, causing big downpours, is also pulling moisture from the land and creating big droughts. And indeed, when we think about global water use, 12% domestic, about 20% industrial, and about 70% is agricultural. So this is the breakdown. So global water use underpins agriculture, underpins food, and separating out water, food, and energy is impossible to do. And they're all interlinked, and they all interact with global climate change. So this is global freshwater use over the last 100 years or so, and you can see again exponential increases in the volumes of water that are being consumed and used globally. And so again, big water stress into the future for us. And of course, water interlinks all sorts of areas of use, of runoff, drought, sea level, interacts with industry, domestic water use, and agriculture and energy. So we're getting less water in places where we've not had it before, too much water in others, and then we're getting increased demand from society. So big problems there in terms of this. So our water use increases as temperature rises, you would imagine. And this is having all sorts of effects in terms of our water bodies globally. I'll show you one example, Lake Chad. I did a project on this when I was an undergraduate as it was drying up. Profound impacts in terms of water use and resource in that area of the world. And water is incredibly important in terms of the diet that we produce as well. So, over 100 liters of water is needed to create the 1 kilogram of beef, I think it is, 1 gram of protein. So 1 gram of beef takes 112 liters of water. Think about the volumes here, it's incredible. Sheep or goat meat, 63 liters for a gram. So real big impacts in terms of the water that's needed to produce the protein that we consume. So big linkages here. And we're already seeing some of these trends. So particular parts of the world, what we're looking at is surplus and deficit of food production here in millions of tons net trade. So North America producing significant volumes of food, South America growing, but there are large areas of the globe where actual food production or food deficit, I should say, is increasing. So the amount of food that's needed to be imported into Africa and Asia is increasing all of the time, and lots of that is related to changing patterns, both in terms of finance, but also in terms of the impact of climate change on that finance. And we're seeing warmer temperatures already reducing yields of wheat and maize and barley in low latitude regions. So what do you think, just moving back out into Menti, what do you think the the reduction is. So what's the projected decline in crop yield for every 1 degree of warming? So what percent of declining crops do we get for every 1 degree of warming? So we've had 1 degree of warming already. How much do you think our crop yields will decline as a result of each degree of warming? So this links into the IPCC, of course, who are talking about 1.5 degree of warming being the target that we should aim for. So we can see here we've effectively got, again, we'll come back to this as they're coming through. So around 5–10%, yeah. So that's really good. Those of you that managed to get to that, you're not far off. So corn for every degree of warming, 7%, wheat 6%, rice 3%, and soy around 3% as well. And those 4 crops are 2/3 of human calorie intake. So incredibly important crops for in terms of food security. So for every 1 degree of warming, we're wiping out that production. And what that means is that essentially we're going to have areas of the earth that are actually completely uninhabitable in terms of being able to produce food in those locations. And you can see, I'll just toggle between the two here, the areas that become uninhabitable as a result of climate change. Think of the population of India, think of the population across Southeast Asia, across the Middle East that are impacted by this. And some will argue, I think it's a stretch, but it's an interesting talking point which I thought I'd put in here, is that we're already seeing the effects of this. Global climate change was attributed in a number of studies to food insecurity in Syria, that many believe drove the civil war there, or certainly a catalyst for it, and indeed, you can trace all of that through in terms of migration of people and impacts on policy and politics, right the way through to things like Brexit even. So the big geopolitical pieces here. I think this is a little bit of a stretch personally, but some people have made that argument. But when you start looking at things like this, where population of India, large swathes of India become uninhabitable as a result of climate change, you really start to think about the impacts that a small trickle of people from the Middle East across Europe had a few years ago, to the mass movement of people that will be driven by global climate change into the future. And indeed, it's right up there in terms of the risk register of lots of countries. I want to finish off by just working through some carbon things and then looking into the future. So what we've got here is how much CO2 different countries have produced. So the cumulative amount. Of course, we drove the Industrial Revolution in the United Kingdom, so we start off with a head lead over everybody else, I guess, if you want to think of it like that. And so since 1970, how much CO2 has been emitted by these different countries? And you can see here, the US at the turn of the century really beginning to boom. Lots of emigration to the Americas, and it takes over around the start of World War I. And begins to accelerate in terms of productivity and production as we move through. You can see some of the other countries just popping up at the bottom here. So the Soviet Union moving up in terms of its output post-war. So Germany kind of in decline around there, but then recovering. USA continues to lead the world in CO2 emissions. Soviet Union, right in the middle of the Cold War, really begin to grow in terms of their emissions. We are increasing very slowly, but look at the rise of China in terms of the last few years, as China really expands its industry, its sector, and begins to push out. So this is cumulative, and you can see the main players here, in fact, in terms of the impact. So you can see from that the sorts of impacts they have, and you can look at some analyses that have been done to look at when the peak year of carbon emissions was. So these are projections that the peak of of carbon production, of CO2 production for the Soviet Union was back in the 1990s. The USA is just kind of happening, or has happened, or is happening around now. But these other countries like China are really kind of beginning, you know, they're not going to hit their peak output in terms of CO2 until 2030, and that's a real issue for us in terms of addressing this. And particularly when we start thinking about, well, how many years of emissions do we have left? This is a compilation of studies that have projected how many years of the current emission levels of CO2 do we have before we tip over into IPCC territory of the 1.5 degrees. And you can see, you know, that these are from models, observations, projections, etc., a range of studies. And you can see, you know, if you average all these together, they reckon around 10 to 15 years maximum in terms of the emissions levels that we've got. So we've got 10 years of emissions of CO2 to really address at the level we emit now the global climate crisis. And of course, you know, the World Resources Institute have kind of run a series of models to kind of look at this, at the pathways to achieve net zero. And these basically show the longer we leave it, the harder it is to really drive down. The decline that we need to make is much harder. So if we'd have been able to do this back in the mid-90s when this was called for, it's a far easier transition than the transition that faces us now. But what's really interesting is the way in which global finances work. So what I'm showing you here is time on the bottom axis, demand on the x-axis, and what we've got is incumbent technology. We'll call that fossil fuels for now. And what's interesting is when you reach peak demand, we have this new technology here, renewable energy, starting to grow up. And what finances are worried about is what sits in here is called stranded assets. It's when you've invested in this continued increase here, but you don't get the return because the value of what you've invested in drops off as it's challenged by something new. And this is really the crux of, I think, where we're going to address the global climate crisis into the future. So if you have a look at the energy sector returns over the last few years, clean energy companies, their return have been massive compared to fossil fuel companies, and the price of oil and the impact there. So the investors are starting to change the way in which the global finance system works around renewable energy sources. And indeed, renewable energy generation is on an exponential track. I mean, if you're into fossil fuels, renewable energy looks like a coronavirus in terms of its exponential growth and how quickly that's coming through. And you know, we're seeing doubling happening more and more frequently in terms of the output. So I wanted to just have a final one on the Menti here, which is how many times more wind power is installed now than we predicted in 2000 is the question. So let's go back. So how many more times wind power is installed than we predicted back in 2000? Okay, so a few coming through there. So, you know, 5, 10 times more, 15 times more, or 20 times more. So we'll leave that there for a moment and shoot on. Actually, it's 20 times more. So yeah, colossal increase in installed capacity. This is a linear a log plot here. You'll have come accustomed to these looking at infection rates from coronavirus. This is the non-log plot, and you can see this is the world curve here, the massive exponential growth here. This is 95 to 19 on the bottom here, so 95 through to 2019, and you can see over the last few years this massive growth in wind energy, and of course, yeah, it collapses onto a linear plot on a log scale. So massive increases in wind capacity. And where's that happening? Well, this is back in 2000, and this is now. So you can see the countries that are really installing wind power: China, US. We are, in terms of the size of us per capita. Germany, a big player as well. So there's lots of wind power generation being installed, and colossal volumes, and lots of potential elsewhere as well. And of course, that's driving down the cost. So per megawatt hour was over 200 euros back in 84. Now you're down to tens, if not single digits, in terms of the cost per megawatt hour. And last year you'll seen that we had record number of days without CO2 being emitted from coal-fired power stations. Indeed, last year 18 times as much electricity came from renewable sources as it did coal in 2019 across the UK. So we're on the cusp of a real big transition in our energy system, and all the things that are happening in the Humber in terms of offshore deployments, and Hornsea 1, Hornsea 2, Hornsea 3 and 4, the biggest wind farms in the world, are being deployed out of the Humber estuary, which is absolutely awesome to be at the centre of that, and a knowledge economy that all sits around it. It's what the green economy looks like, and it's happening right here in the Humber. And it's important because 40 times over is the amount of energy that wind could provide us if we tapped it all. And so there's massive resource there. It's just a matter of going out there and tapping into it. And the same sort of things happen with PV, so photovoltaics or solar. The cost has declined massively to pence now per watt, when back in when I was born it was $80 a watt, which the reduction's just incredible. And of course what you've seen is massive reductions in massive increases in terms of installation since 2010. Again, cumulative gigawatts of energy installed since 2005, really taken off, and has been driven and driving that price reduction as well. And there's enough solar energy reaching Earth every single hour to fill our whole energy needs for a full year if we can capture it. So the renewable sources are there. It's just a matter of us breaking the finance to it and working through how we store that energy as well. But that's for another day. And the forecasts are that this is going to continue. So by 2030, the amount of installed new capacity from renewable energy is going to it's going to absolutely be dwarfing the investments in fossil fuels. And again, in Europe, what we're seeing is new energy capacity. Very small amounts of coal being invested in still, but most of it now is wind and solar, which is great to see. Now, to finish off on a few things, just to say that in Hull and the Humber, yeah, we're doing all of the things around offshore wind and growing that economy out, which is just fantastic to see. But we have a big industrial sector, and we're on a journey within Hull and the Humber to net zero, and that means changing our economy, looking at hydrogen as a fuel and a storage system. And there's loads of research on the renewable sectors now going on in decarbonizing the industrial cluster that sits in the Humber. It's the biggest industrial cluster in the UK in terms of carbon emissions. So we crack it here, then we'll be cracking it for the rest of the world, and in terms of what we can achieve. Of course, the University of Hull's right in the centre of that. The Aura project that's really shaping the future of offshore wind and low carbon decarbonisation for the region, with a new building, lots of collaboration with industry, and all the skills and the training that the university can offer in terms of masters and undergraduate programs to really feed this growth in green jobs that's coming. There's hundreds of thousands of jobs in the green sector that are going to be needed over the next 10 to 15 years. And as a university, we need to be addressing that and skilling the people and the leaders that will shape this sector into the future. And finally, I wanted to finish on a more somber note, just around coronavirus and the impacts that's had. And I think of the reason for doing that is to really put into perspective the challenge that is laid before us. So we basically got here a plot of the impact of world events on CO2 emissions. So the financial crisis of 2008 knocked back economic productivity and took out around 500 gigatons of carbon from the emissions. As we move through the impact of the Second World War, here you can see the sort of scale of impact of the percentage drop of CO2 emissions globally, around 2% reduction. The predictions here for coronavirus is around between 6 to 10% of 2020 emissions will see a reduction on the gross total for 2020. Of course, coming from that period of lockdown from January in China through to midsummer in Europe. So a 6 to 10% drop from shutting down large sections of the entire global economy. We need to do that every single year between now and 2050 in order to decarbonize our economy. And I think that puts into perspective the challenge and the reason we need a rapid transition to renewable energy into the future, because it just shows you how difficult this problem is. And it's the greatest, I don't joke when I say it's the greatest challenge that humanity's faced, because we shut down large swathes of the global economy and we manage 6%, and we've got to get to 100 by 2050. And we've got to get there quite quickly as well to make sure we're on the right trajectory to reduce the emissions. And again, that kind of puts into perspective that we have this kind of reduction, financial crash as we move forward. What does this look like into the future in terms of the next phase as we roll over? So with that, I want to finish. I want to thank loads of the slides here came from the Climate Reality Project, a fantastic resource for anybody looking there in terms of the science of climate change and trying to pull content together that's engaging. Lots of stuff from NASA. Our World in Data is a fantastic resource that plots up all sorts of data in different ways that I was able to show you. ESA imagery, things from British Antarctic Survey and photographs there, the Carbon Brief and also NOAA in the US, and finally the University of Hull's marketing communications team for all the help and support of setting all this up.